Good morning, students. Myself, Dr. Shantani Bhattacharya, Assistant Professor of EC Department, SRM Institute of Science and Technology, Kattankulathu, Chennai. Today, in my lecture, I am going to start lecture 3 of the digital logic gates. If you didn't follow my previous video, I request all of you, please follow my previous video. It will be helpful to understand all other this rest of the part. Okay. So today I will actually giving a lecture based on what is universal logic gate and why NAND and NOR gate act as a universal logic gate. So starting with what is universal logic gate. So universal logic gate is a gate which can implement any boolean function without need to use any other gate type. Okay. So basically here NAND and NOR gate are used as a universal logic gate. Basically we can design any type of logic gate by using this NAND and NOR gate. So it is called the universal logic gate, and like that AND gate is typically implemented as a NAND gate followed by an inverter, and also OR gate is typically implemented as a NOR gate followed by an inverter. How it is, I just explain in the next slides. Okay. So this is actually why NAND gate act as the universal logic gate. One by one I will explain. Okay. So starting with NAND gate as an inverter. So here you can easily understand this is actually, all of you know, this is actually the NOT gate symbol. If you didn't know why it is called NOT gate, so please follow my previous video. Everything is explained properly. Okay. So in a NOT gate, if I give as the input A, then output will be A bar. So here actually by using a NAND gate we will basically design this NOT gate. So here we can see that in the NAND gate both the inputs, basically NAND gate are two inputs. So here both the inputs we are shorted and giving a input A, so output will be A bar. So actually how it is happened, I am just going to explain by this writing something. So here actually first of all this is actually the NOT gate symbol. Okay, so this is A, this is A bar, and NAND gate means this is actually NAND gate. So if I'll give A and B here, so it is actually A B bar. Okay, so like that, if this is actually A. Okay, so here if I design a truth table 0 0 0 1 1 0 1 1, in that case if this is A, this is B, this is Y is actually A dot B bar. This is actually in any other combination except 1 1 combination, the output will be 1. Only when both the inputs, that means A and B, when both the inputs are 1, then only output will be 0. Only this condition output will be 0. So now if I consider this NAND gate, both the inputs are A. So if I am giving, or if I can write this diagram in this way also. Okay, so both as a, so I can short this both the input and then giving A. So here also the same thing is happened. Here in both the inputs A is going. So how here actually I have already said it will come A bar. How? So actually here A means actually this is represented as 1, because here actually 0 is represented as A bar and 1 is represented as A. So here in both the input it is A, that means is equals to 1 equals to 1. That means both the input of the NAND gate are 1. So output will be 0. 0 means A bar. So this is actually indirectly we can form the NAND NOT gate in terms of NAND gate. So this is actually, I hope all of you can understand why I am giving this type of figure. Okay, now coming to the next part, that how we can design AND gate by using a NAND gate. Okay, so here also, first of all, I am using a NAND gate where both the inputs are A and B, so output will be A B bar. So this is very common, we all know that if I am giving A and B, output will be A B bar. So after that, here actually we have to produce AND gate. So output, if input is A and B, then output will be AB. So this is actually the thing. So AB bar we have got, then after that we have to pass this AB bar through a NOT gate. So this is actually the NOT gate. NOT gate is actually, it is in the form of NAND gate. This is actually the representation of NOT gate in the as a NAND gate. So after passing through this NOT gate, it will come AB bar whole bar. That means according to the Boolean law, AB bar whole bar is actually AB. So we will get, that means we are giving A and B, so output will be AB. Now coming to the next part, that means we have to design OR gate by using NAND gate. How? So here basically this is the NAND gate number 3. So here both the inputs are A bar and B bar. Okay, so we cannot give directly A bar and B bar, so we have to give one and that means A and B through a NOT gate, and that means A, that means through a NOT gate which is represented as NAND gate. This is G1, so it comes A bar. Similarly, input B which is passing through another NOT gate which is represented as G2, and it is actually represented as by NAND gate, and then it comes B bar. So after that, these two A bar and B bar input passing through this G3 NAND gate, and it will come A bar B bar whole bar. So it will come A plus B. Okay, so actually how it will come, there is some simple mathematics is also there. So I am just quickly going to explain why this will come. Okay, so here actually this is actually the OR gate. This is OR gate symbol. This is A, this is B, this is A plus B. Okay, so now we have to represent this OR gate by using a NAND gate only. So first of all, we will, I have already said that we cannot give directly A bar. So this is A bar, then again passing through B through a NOT gate which is represented as NAND gate. This is B bar. After this, then we will pass this to another NAND gate. It will come A bar dot B bar whole bar. Okay, now the mathematics is A bar B bar whole bar. So first of all, we consider A bar equals to X, okay, and B bar equals to Y. So what is actually the output if I consider Y equals to this? So Y equals to this, so Y equals to actually X and Y bar. So according to the De Morgan's law, if I break this according to if I apply in this equation De Morgan's law, it will come X bar plus Y bar. Now we have to put the value. What is X? X is actually A bar. So this is actually A bar whole bar. Then what is Y? Y is actually B bar. So it is B bar whole bar. And according to the Boolean algebra law, something, any variables bar over bar, it is actually the original variable. So it will come A plus B. So we are giving input A and B, and then output will be AB. So this is actually the representation of the OR gate by using a NAND gate only. Okay, then again we will design NOR gate by using a NAND gate. So this is very simple. NOR is actually OR plus NOT. So up to this, this is okay. This is actually you are forming a plus B. Then we have to pass this A plus B through a NOT gate. So this is actually the NOT gate, which is actually G4 is actually represented as NOT gate by using only a NAND gate. So after passing A plus B through a NOT gate, which is represented as NAND gate, it will come A plus B whole bar. So this is actually the NOR gate, which is represented as, overall this is the representation of NOR gate by using a NAND gate. Now I am coming to the same thing, like that we will use the NOR gate as a universal logic gate, because we will design NOT gate, OR gate, AND gate, NAND gate, all these gates only by using NOR gates. Okay, so same thing we will follow. So here this is the NOT gate representation. So similarly, this is actually the NOT gate symbol. Here both the inputs we are basically shorted, and then input is A, so output will be A bar. Similar the NAND gate. So now I am coming to the OR gate section. How we will design OR gate by using a NOR gate. So here also input, first of all input I am giving A and B. So after a NOT gate it will come A plus B bar. So when we will pass this A plus B bar through another NOT gate, then it will come A plus B. So this is actually the nothing but representation of NOT gate by using a NOT gate. So this is A plus B. Okay, now I am coming to explain how we will design the AND gate by using a NOR gate. Okay, so like that, similarly here also we cannot give A bar directly, so we will give A through the NOT gate. So this is NOT gate, G1 is actually NOT gate, it is represented as a NOT gate. So B also, this is represented through the NOT gate. We passes, then it will come B bar, and finally this 2 A bar and B bar is actually the input of the another NOR gate, that means NOR gate G, and it will come A bar plus B bar whole bar. Okay, so now I am again going to explain this mathematics again, so then it will be easier for all of you. So actually first of all this is A, then I am passing this A through a NOT gate, so it will come A bar. Okay, then again I am passing B through another NOT gate. When that means this is actually a NOT gate represented as NOR gate. Okay, so this is actually B bar. Then we will pass these two input through another NOT gate. It will come A bar plus B bar whole bar. Okay, so if I consider y equals to A bar plus B bar whole bar, then just at that moment y is equal to, I just write A bar plus B bar whole bar. So first of all we consider that means A bar equals to X and B bar is equal to Z. Okay, so it is actually X plus Z whole bar. Okay, so according to De Morgan's law, it will come X bar dot Z bar. So now we put the value of X. X is actually A bar, then again bar, then again Z is actually B bar, then already there is another bar, so whole bar. So it will come A B. Okay, or we can represent A dot B. So actually we have to design a NAND gate, that means NAND gate A, our input is A and B output is AB. So this is also came the AB. So basically we are using the NOR gate for representation of the AND gate. Okay, now I am coming to design a NAND gate for by using a NOR gate. So first part of the design of AND gate is similarly the the same thing, okay, because first of all we have to, for designing a NAND gate, first of all we have to design AND gate, then AND gate input we have to pass through a NOT gate, okay. So here is actually the NOT gate, which is here represented as by NOT gate, then it will come AB whole bar. So thank you students, I hope all of you understand today's lecture. If you have any doubt, then you can give me this doubt in a comment section. I'll try to solve definitely. Thank you so much.